Hello and welcome to this video. In this video we're going to be looking at the diffraction experiment. Now what I'm going to be investigating in this experiment is how the wavelength can be measured using diffraction techniques. Now obviously this probably isn't always going to be the case for everything that you do in a lab, but this is how I'm going to approach it. The setup will be the same, it's just the investigation and the outcome of the experiment that will change. But most people will usually use a diffraction experiment to measure the wavelength of a laser. And we can do this in two ways, so I'll go through both of them because you will end up usually doing both. So the first one is we can do diffraction via a double slit. Okay, so this will be Young's double slit experiment. And with a double slit, what we're going to say is that our equation is that usually we say omega is lambda d over s. Now what we can actually say is if we want to know lambda, then we can rearrange this for ws, lowercase w, s over uppercase d. So this is the equation that we actually want. Okay. Now, our diffraction setup is the same as it would be theoretically. You're going to end up with a laser over here that is going to fire through some slits. Now slits will usually come in like a square thing like this, and it kind of looks like there's a filter in it, and you'll see two very small white lines and it will look something like that. And they usually have like a sticker up here that will tell you the distance between these two slits, so that S is already known. So S can be read from the slits. Okay, so you can look straight away up here and usually be able to figure out S, and they will usually also state the uncertainty on them. If they don't, then you assume there is no uncertainty on them. If you were doing an experiment where instead you know the wavelength of the laser and you wanted to work out the value for S, you could also do that by just rearranging this equation for S and then measure everything else the same way. But we're going to have a laser of some unknown wavelength. It will usually be a red laser because they're not that dangerous. And the laser will fire some light towards these slits. So this is, let me actually draw them as slits. So it will look something like this, and then you will have a screen some distance away where this distance here is S that you can read from the slits. This distance here is D. Now D can be measured with a ruler because your value for D needs to be quite large, and the reason you want D to be quite large is because you want W to be quite large in order for you to have a more accurate reading, because you'll find that if you have a really small fringe spacing, your uncertainty is going to be a very high percentage of the actual measurement that you take. You want to have a large distance so that you have large fringe spacing so that your uncertainty or your percentage uncertainty gets reduced. So you want to measure this with a ruler, so it should be greater than 1 meter at least. Okay, obviously the bigger the better, but you're limited by the space that you have. So you measure D with a ruler. Again, stating the uncertainty on this ruler is always going to be 0.5 millimeter, unless you have a super ruler. Then you're going to end up with fringes on this thing. So let me change color so I can represent. This is a red laser, so I can actually do this in red, like this. Then it's going to spread out, and I'm going to get a bright peak in the middle here, and I'm going to get subsequent maxima either side, and they will be equally spaced by W. So this value is W. Now I would recommend taking multiple measurements of W in order to get a more accurate reading. But W, you're actually going to measure with a micrometer or a verniers caliper. Now, personally, I would measure with a verniers caliper. I feel like that would make it much easier, measured with verniers caliper. It would make it a much easier measurement to do, and it would reduce your uncertainty by quite a bit. How you measure this is completely up to you. Usually what I would recommend is that this screen be some sort of paper that you can draw on. So you can basically then mark where the dots are, and then you can take it away and have it down in like a more comfortable position for you to read in, or a more accurate position for you to read the measurement in, so that you can actually get a good reading. Because if you're having to lean over a table and then kind of lean towards the wall and then hold it over, but make sure you're in the right space so that you don't block the light and you can still see it, it's basically going to cause loads of uncertainty that you don't need. So just mark it with a pencil and take the paper, and then you can measure the distances on the paper. But like I say, you want to make sure you get as many measurements of W as possible, and you can do that because you have multiple fringes. Okay, so now you know D because you've measured it with a ruler, you know W because you've measured it with vernier calipers, you know S because you read it from the slits, and now you can calculate a value of lambda. And this will effectively be your answer. This isn't a very difficult practical by any means. The only possible thing that could be quite difficult is doing your error analysis of this. But your error analysis is just going to be, because you're multiplying and dividing things, you're just going to add together all your percentage uncertainties. And if you remember, the percentage uncertainty is just the absolute uncertainty, which is just half of the resolution. So your absolute uncertainty divided by your actual measurement that you've made, and then times that by 100 to make it a percent. Okay. So this is one way that you can measure the wavelength of the laser. But it's not the only way. We could also get rid of this value of S, and we could put in, instead of double slit, we could put in a diffraction grating. So let's have a look at doing this via a diffraction grating and see how that would be different. So if we put in a diffraction grating, diffraction gratings will usually not have a value for S. They will usually be rated. So for example, you might have 500 lines per millimeter. This would be a very small value for S. So you might have 500 lines per millimeter. This you can read from the sticker again. Yeah, so your diffraction grating will look very similar, but you probably won't be able to see the lines on a diffraction grating because they'll be much too small. So diffraction gratings, you'll usually just read the sticker, and they'll give you some rating like this, and that will allow you to then work out the value of S. But in this case, we're not going to do the same method. It would be pointless doing the same method as before, because then what's the point of switching it out? What we're going to say in this case is we came up with an expression for diffraction gratings, which was that D times sine theta is equal to N times lambda. Okay, so this is the expression that we're going to use in this case, which means lambda is actually going to be D sine theta divided by N, where N is the order of maxima. So our setup is going to be very similar. Let's first work out D, if this is the case. So that means D is 1 millimeter, which is 1 times 10 to the minus 3, divided by 500. And that means that D is actually 2 times 10 to the minus 6 meters. So we know D, okay? There will be some uncertainty on this as well, but we'll worry about that later as well. So we know D. We also need to know this angle of theta, and so what we're having is the same setup. We'll have a laser here. In order to verify that both these methods work, I would recommend using the same laser so that you can get, you should end up with the exact same result because the wavelength wouldn't have changed. Although you will get some variation depending on how long the laser's been left on for, because it will reach different modes. But for the most part, it shouldn't be a drastically different number. It should be roughly the same. Okay, so we have a laser. We're now going to fire it at a diffraction grating, which I will note like this. We're going to have a screen that is going to be a big distance D away, but we don't have to know the distance in this case. Then we will end up with these maxima and minima like last time. So we have the laser incident here. We're going to end up with a central maxima and subsequent maxima and minima. Okay, and in this case, n, this is 0th, this is first, this is second, this is first, and this is second. So I did say that we don't have to know d. However, it's practically impossible to measure the wavelength straight from this, since we don't actually have specific waves that are traveling in this distance. This theta that we've made is based on the ratio of the distance and the fringe spacing. So if we called this distance w again, and then we called this distance between the slits and the screen d, that means that sine theta, this is theta here, okay? Tan theta is going to be w over d, because it's opposite over adjacent. And what we're actually going to use is something called the small angle approximation. Now, in order to measure sine theta, there are multiple ways of doing it. So you can physically do it if you want to. You could measure specifically the distance from the slits to each maxima, and that would give you this actual distance, and then you could do the trigonometry from there. However, we're not expecting this angle to be very big. Obviously, the bigger d is, the smaller the angle, or actually the angle will be the same, but the bigger d is, makes w bigger. So because we're expecting this angle to be quite small, we can say that for small angles, sine theta is approximately the same as tan theta. Okay, now you can check this for yourself, but this is what we call the small angle approximation. I think I've mentioned this in a previous video as well. So we can do the same as before and measure the fringe spacing and the distance between them, or you could measure the distance from the slits to each maxima and then do sine theta would be the opposite over hypotenuse, so that would be w over the distance that you measure between those. So w over, let's call this, let's call it s, why not? Maybe w over s, okay? But you'd find that s is going to be basically not that different from d, since you're only moving like a few centimeters over, so they're roughly the same. So you can use this small angle approximation to make them the same, and then just measure w and d. The eagle-eyed amongst you will notice that if I actually put this expression in for sine theta, then lambda becomes dw over d n, and d is the same as s, so I end up with the same expression I had before. So they are a very similar experiment because you haven't really changed much but the diffraction grating. But this n means that it does matter which maxima we're looking at. If we're looking at the first maxima, then this is just dw over, dw over d. If we're looking at the second maxima, then w actually becomes this full thing. So let me call that w2, let me call this w1. But that just means we already know this fringe spacing is going to be the same. So if we're then saying we got the second one, we're dividing it by 2, so we get the exact same thing. So the point I'm trying to get across here is that this is the exact same method as what we just did. The two equations are identical. They just have different applications in different cases, but the two equations mean the same thing. They're just written in different ways. But the process of carrying out both experiments will be identical. In both cases, you'll get a laser, you fire it at slits, the slits will then project a diffraction grating, a diffraction pattern on a screen. The screen, you then need to measure W using vernier calipers, you need to measure D, the slit screen distance using a ruler, you'll measure S or small d by looking at the sticker, and then use the equation that you have to rearrange for lambda, okay? That will then tell you your wavelength of your laser. And again, both of these wavelengths should be exactly the same because it's the same laser, so it's going to produce the same wavelength. Okay. If there is some variation, you can just explain that the longer you have the laser on for, it will heat up, and the way lasers work is they have a cavity inside the laser that basically forms a stationary wave inside, and that stationary wave will form a different frequency if you allow the temperature to build up a little bit. So you can say it's reached a different modal frequency inside the laser, and hence you have a slightly different wavelength. It's not going to work if you have a wavelength difference of like 100 nanometers, but if it's like a few nanometers or 10 to 20 nanometers, you're roughly okay. Okay. Now this is the diffraction grating experiment. Thank you for watching.